Okay, so this is another integration technique example that I'm doing. In this case, I'm going to be illustrating trig substitution. So we have the integral of x squared over the square root of 2x minus x squared dx. So first of all, the expression in the denominator should automatically kind of lead you to what your next step is going to be. And you don't necessarily know that it's trig substitution yet, but that expression down there in the denominator underneath that radical is just screaming to you to complete the square. So I'm going to complete the square on 2x minus x squared. So I'm going to factor out a negative 1. And when I factor out that negative 1, that's going to turn that around. That negative x squared is going to become positive x squared. And that positive 2x is going to become negative 2x. And now to complete the square, I'm going to take half that negative 2, which is going to give me negative 1. And the negative 1 squared is going to give me positive 1. So I'm going to add 1, turn right around, and subtract 1. All that underneath the radical, and all this dx. Okay, so this is the integral of x squared over the square root of, have that negative 1 out there, times this first piece right here, x squared minus 2x plus 1. That is a binomial squared, so that is x minus 1 squared, and then my minus 1 out there. All that dx. So this is the integral of x squared over the square root of. If I distribute this negative 1 in here now into both of my pieces inside the brackets, then I'm going to turn this around. Negative 1 times negative 1 becomes positive 1, and negative 1 times x minus 1 squared becomes minus x minus 1 squared. All that dx. Okay, so that looks much nicer for different things that we may have to do with that as we go along here. So first of all, I know it's not going to be a problem that involves inverse trig functions because first of all, my denominator, the expression down there is backwards, and second of all, I have an x squared up top, so I know I'm not going there. But I do have something squared, an a squared, minus a expression that has a variable that I have as a perfect square, x minus 1 squared. So I do have an a squared minus u squared. That kind of expression leads you to something that involves a trig substitution. So I'm going to draw my triangle over here. I'm going to label my angle theta here. Now, I have an a squared minus a u squared. So usually what you want to do in your picture there is whatever you're calling u, which is u squared, which is x minus 1 squared. So that means that u is x minus 1. So that is usually what you want to call, when you have an expression like this, the opposite side. This is one that's going to fit where you use the sine theta. There's some basic rules you got to memorize, and something that fits the form a squared minus u squared, whatever your quantity is squared that involves the variable, which in this case is x minus 1 squared, that is what you want to call your opposite side. And then your hypotenuse is your constant, which in this case is 1, and so 1 squared is still 1, so that side right there is just 1. Alright, so I'm using the square root of both of those. Square root of 1 is 1, and the square root of x minus 1 squared is x minus 1, using just a and u over there. Alright, so that leads me to finding my adjacent side from theta, which is going to be, using the Pythagorean theorem, 1 minus x minus 1 squared. Just doing the Pythagorean theorem, and then taking the square root of that. Which is nice, because I have that in my integral over there. So now, I have 3 pieces over here that I have to take care of. I've got to take care of x squared, I've got to take care of the square root of 1 minus x minus 1 squared, and I have to take care of dx. I've got to take care of all 3 of those pieces using my triangle over there. So first of all, what I have is, I have that the sine of theta is x minus 1. So that means that a couple of different things. First of all, that sine theta plus 1 is x, and so over there in my integral, that means that the sine of theta plus 1 squared is x squared. So I can take care of that. So we'll go ahead and write our next line here. So we have that the integral x squared becomes the sine of theta plus 1, that quantity squared, and we'll deal with that in just a minute, over, now back up here in my picture, I have, looking at my picture over here, I'll do this in blue. But I have that my adjacent side is the square root of 1 minus x minus 1 squared. So I can use my triangle that I have over there, and that tells me that the cosine of theta is the adjacent, which is the square root of 1 minus x minus 1 squared, over the hypotenuse, which is 1. So cosine theta is the square root of 1 minus x minus 1 squared. Alright, so I can get rid of my denominator as cosine of theta. Now, the next thing I still have to get rid of is dx. So, come back up here, I'll do it in red again. But what I have is I have that the sine of theta is equal to x minus 1. So that says that the sine of theta plus 1 is x. So if I take the derivative of both sides, respectively, then take the derivative of sine theta plus 1, you get cosine theta. Take the derivative of x, you get 1, or you get dx. Okay, so I took d theta of both sides of that. So I end up with cosine theta over there on the left-hand side and then dx over there on the right-hand side. Just take the derivative of both sides. Derivative of x is 1, and derivative of sine theta is cosine theta. Use the variables respectively there. So I get that dx is cosine theta. So I can replace dx with cosine theta d theta. So I have a cosine theta and I have a d theta right there. Okay. Alright, so I can replace dx with cosine theta d theta. Okay, so now, let me back up and make sure you understand what I just did right here. I kind of glossed over that, but I took the derivative of sine theta plus 1 equal to x. I took the derivative of both sides of that with respect to theta. So I did d theta of x, which is dx, and then I took the derivative with respect to theta of cosine theta, which is cosine theta d theta, just like you do when you are doing some u substitution to get that expression there. Okay, so my cosine thetas cancel in my problem over here. So what I have is I have the integral. You got to take care of everything over there. You got to take care of everything that has x in it and dx. Do not forget about dx. That's the one piece that people tend to forget, but don't forget about dx. You got to use your expressions over there to get rid of dx. All right, so what I'm left with is the sine theta plus 1 squared, all that d theta.